welcome back. In this lecture, I will continue my discussion on thermal properties of polymers. In the last slide of last lecture, I went through the different factors which can influence the value of Tm, and I discussed that with increased chain stiffness and with increasing the intermolecular attraction between polymer chain and with having a simpler structures which enable better packing will increase the Tm, because these factors actually help in crystallization process. Now, I will give you some examples. In this case, let us compare the value of Tm where R is given by this. If you compare between a aliphatic chain and a aromatic group, obviously this is much stiff because of possible single bond rotations in this case, which is not possible in this case, and stiffness goes up drastically. As a result, Tm will also go up. Similarly, if we go from this to this, we are increasing the stiffness even higher. So, we should expect that Tm should even go higher, but if we compare this to this, we are introducing much more flexible groups, hence the Tm should come down. But if you go from a single bond to double bond, then we are introducing more rigidity, more stiffness, because this will not, the single bond rotation around single bond is not possible in this case. So, Tm should even go up in this case. So, if you look at the numbers, this is 50 degree centigrade, drastic increase in Tm to 70 degree, further increase, then a decrease, but there is a huge increase in the value of Tm, because the backbone stiffness increases in these cases, which result in the higher value of Tm. In this example, we will basically combine two factors, backbone stiffness and polarity. Now, if you compare between a amide group and a CC bond, obviously CC bond will be more flexible, because the single bond rotation is much more possible, much more feasible in this case. So, if you compare between these three polymers, then this, as we increase the number of CH3 group, this will be much more flexible or less rigid, or indirect way we can say that this is the most stiff polymer among these three. Similarly, as we go and increase the number of CH3 group, we are also decreasing the weight fraction of CONH2 in the polymer. Now, these groups actually increases the intermolecular attraction because of hydrogen bonding present possible in amide group, between the amide groups. Hence, going from this molecule to this, we are also decreasing the polarity and intermolecular attraction between the polymer chains. So, both the two factors are working in sync, hence the Tm should be expected to go down as we go from this polymer to this and then. So, let us see the number. So, this is around 110 to 200 degrees, so 52 and 42 degrees centigrade. Similarly, if we compare symmetry and melting point, we can see that if the molecule has much more molecular symmetry, in this case there is a highly crystalline, but in this case the symmetry is lost, one is hydrogen, another is Cl. Similarly, in this case this is Cn and H, and if they are atactic, then it has a very low degree of crystallinity. If they are isotactic, there is a possibility that it will have crystallinity. Similarly, if we compare between these three, this is non-symmetric. So, it is not crystalline, and this is having much more symmetry and simpler molecule. Hence, the feasibility of this molecule to undergo crystallization is much more compared to this. Hence, the Tm for this is much higher than this molecule. So, basically again I am stressing the same points again and again, that stiffness increases the Tm, the intermolecular attraction increases Tm, and molecular symmetry, regular structure also increases Tm for polymer chains. Molecular weight also influence Tm, but beyond a certain molecular weight it tend to level off. In this case, this is a data for N alkanes up to C 100. So, you can see that after about N about say 80 or something, and it basically kind of levels off. And generally the type of molecular weight we use in commercial applications for the synthetic polymers, the molecular weights are quite high. So, the dependence of molecular weight, the dependence of Tm on molecular weight in that range becomes less important. Now, we will discuss the crystallization process. Crystallization is the process whereby an ordered structure is produced from a disordered phase, and disordered phase could be from a polymer melt or a polymer solution. Most cases, of course, we deal with polymer melt, and we talk about crystallization process from polymer melt. So, when the temperature of the polymer melt goes below the Tm, the random tangled polymer molecules in the melt, they tend to become aligned and form small ordered regions, and this formation of small ordered regions is a process called nucleation, and the ordered regions are called nuclei. So, the process of forming these small ordered regions are called nucleation, and the ordered regions are actually called nuclei. And once this happens, then growth happens in the next step, where more and more polymer chains come and basically form crystal on the nuclei, just like when you talk about crystallization of small molecules as well. So, in the next step, which is growth, the crystal nuclei grow by addition of further chains to the nuclei. So, crystallization has two distinct steps. One is nucleation, where formation of nuclei, and next is growth. Nucleation can be homogeneous or heterogeneous. In case of homogeneous nucleation, small nuclei form randomly throughout the melt, whereas heterogeneous nucleus take place on foreign bodies such as dust particle or walls of container vehicle, and sometimes we deliberately add some external agents which are called nucleating agents, which basically act as the point where nucleation can take place, because polymers are mostly polymer crystallization happens mostly through heterogeneous nucleation, not through homogeneous nucleation. And the substance which are added to induce crystallinity is, or to induce nucleation process, we call nucleating agent. So, crystal develops via nucleation and growth mechanism, as we discussed in the last slide, and as I discussed also that nucleation in polymers are typically or generally heterogeneous, and we add nucleating agents to induce nucleation in polymers. Now, rate of crystallization in polymer samples depend on polymer mobility as well as driving force. Now, if we take a polymer sample and then heat it slowly, then above Tg it has sufficient mobility, but if it goes, the temperature goes towards Tm melting point, then the driving force will become lower and lower. So, when the temperature is around Tg, the polymer mobility becomes 0. If we increase the temperature above Tg, then we slowly starts to induce polymer mobility. And when the temperature is close to melting point, equilibrium melting point, then driving force also will become 0. But if we decrease the temperature below the equilibrium melting point, then obviously the tendency to crystallize will be much higher, because the temperature of the experiment is below the equilibrium melting point. Hence, if we increase the temperature above Tg, it helps in crystallization, and if we decrease the temperature below Tm, it also helps in crystallization. So, there is a middle path where it is maximum, middle temperature where it is maximum, crystallization is maximum between Tg and Tm, and there is a particular temperature where generally crystallization happens if we start to anneal a polymer sample, and that temperature is called Tc, or crystallization temperature. We now discuss determination of the values of glass transition and melting point, polymer melting point, and for that we need to probe the physical properties at transition. There are several physical properties which undergo drastic change or discontinuous change at transition, these transitions. For example, heat capacity changes in case of grease continually in case of Tg, and enthalpy changes in case of Tm. Specific volume or density also changes in these transitions, modulus or the mechanical properties, they also changes, refractive index changes discontinuously, heat conductivity changes. So, we can utilize or we can follow any of these properties as a function of temperature to find out or to determine the glass transition temperature and melting point. But generally very two common methods which are used to determine Tg and Tm are differential scanning calorimetry, which basically utilizes the discontinuous changes in either heat capacity of enthalpy with respect to temperature, and other mechanical property, temperature dependent mechanical property, where modulus is followed or monitored with respect to temperature as a function of temperature to find out Tg and Tm. Let me discuss this differential scaling calorimetry first in detail, and later on I will discuss about this property in later lecture. So, in differential scanning calorimetry, in short DSC, this is used to investigate the process that involves changes in heat capacity, second order transitions like Tg, or a change in enthalpy, first order transition like Tm melting. So, studies of crystallization and melting point, measurement of Tg for homopolymers, copolymers, polymer blends can be done using DSC method, and we can also monitor other chemical events like curing, cross linking and some degradation, or if some reactions happen, that can be also monitored by using differential calorimetry. So, any process which basically evolve or generate or absorb heat if in the system, that can be followed using DSC. DSC are actually two types, mainly two types. One is power compensation DSC. In this case, one sample and was inert reference material. Inert means which does not undergo any phase change or any transition in the temperature range where we will do the experiment. So, this in case of power compensation DSC, these two sample and reference material is heated up maintaining a fixed temperature. So, in this case same temperature is maintained and the differential heat input to maintain this same temperature between sample and reference is plotted as a function of temperature. So, in case there is a transition happens which will require either more heat to be supplied if there is an endothermic process, or if it is exothermic process, some heat will evolve by the system. So, there will be less requirement for heat supply from outside to maintain the temperature, and this is followed in case of power compensation DSC, or simply when you talk about simple DSC, this is the method we generally talk. There is another DSC which is called heat flash DSC. In this case, both the sample and reference are heated at a controlled rate. So, they are heated at same rate by supplying same amount of energy, but the difference in the temperature between sample and reference are plotted as a function of temperature. So, if there are any exothermic or endothermic event happen, there will be deviation of this temperature difference between reference and the sample. So, in this method generally also referred as differential thermal analysis or DTA. So, in the first case we generally talk about DSC, and second case we talk about differential thermal analysis or DTA, and we can also both this method as differential calorimetry as well. So, DSC measures changes in the differential heat flow with temperature, keeping same temperature of both sample and the reference. In case of DTA, the heat flow is same, delta is same, but the differential temperature is monitored, delta T is monitored as a function of temperature. In case of phase change, there could be heat evolved or absorbed depending on whether it is a exothermic process or endothermic process. One thing also need to be noticed, if you heat or if you supply heat from outside, or if we at a much rapidly, then the sample may not actually follow this heat flow, because there the sample might require little longer time to actually overlap the heat flow or basically capture the heat properly. So, if the heating rate is high, rapid, then the sample cannot keep with the furnace temperature. So, there could be a error in that measurement, but if we do slow heating, then we can actually have a proper measurement, but there is a risk also in slow heating. If the sample is prone to crystallization, then on slow heating it might crystallize above Tg. As a result, the nature of the sample might change. So, the value which we will get, that may not be reflecting the values for the original sample we started with. So, that is so basically there is a balance in maintained, there is a moderate heating rate is applied in DSC or DTA. Both these types of DSC, DTA or DSC, generally same sample container, small aluminum pans are used, and aluminum pans are used on which aluminum lid can be crimped, so that nothing goes out during the measurement process, and typically 5 to 20 milligram polymer samples are used. Sometimes if the volatile sample, volatile polymer, liquid polymers, liquid samples are used, then we use special hermetically sealable aluminum pans or lids that actually prevent loss of volatiles, which is important. And generally the measurements are carried out in inert atmosphere, light in presence of nitrogen or argon, because if we do in a air, that might do oxidative degradation to the polymer molecules, which will complicate the measurement TG and measurements of TG and TM. So, generally unless it is specifically required, we do the measurements under inert atmosphere of nitrogen and argon or argon. So, this is what a ideal DSC curves look like. So, if we plot the energy supplied and this is the temperature, and in this case we are plotting this side endo. So, at TG the heat capacity of polymer samples changes. So, glasses will have lower Cp than the rubber sample. Rubber samples generally have higher Cp. So, there will be a change in the Cp value of the glass. This is a glass and this is rubber. So, there will be change in the Cp value, and the midpoint of this transition is the value of Tg generally considered. So, if we draw a line from this and another from this side and draw a tangent through this line, and the middle of this point would be your Tg, and this difference is delta Cp, the difference in the heat capacity. So, this is Tg and this is T melting. In the melting process generally endothermic. So, we have a peak towards endo direction, and the area under this curve will give us the value of del H melting or del H freezing, whatever you call. So, this value generally the peak value which is considered as the melting point of the polymer. So, from the single experiment we can get, if the sample is semi crystalline, we can get Tg and Tm. Now, there is another possibility. In this case we are plotting delta E, and in this case this side is endo and this side is exo. So, any exothermic transitions will have going this way. No, this is endo and this is exo, like the before. So, in this case this is Tg, the midpoint of this is Tg and this is Tm. So, this temperature is Tm, and this is process as I was discussing, this is called crystallization, and corresponding temperature is Tc, crystallization temperature. It happens as I discussed between Tg and Tm. So, if you do the heating very slowly, then and the sample is prone to crystallization, then it might happen that above Tg the sample might getting crystallization, and you can get a exothermic peak for that. Crystallization is exothermic process. So, you can get a exothermic peak, and the corresponding temperature we can call crystallization temperature or Tc, and once the crystallization happen, if we heat further, we will get the Tm for the crystal domains which happen. Now, this case, this is exo down, in this case endo down. So, in this case we can see this is Tg and endothermic, this is exo up. So, this is Tc crystallization, and this is melting. So, this is Tm. Now, we can also post melting, we can also use DSC for getting the information about others, like in this case we are talking about cross linking, and this is maybe evaporation or vaporization of polymer. And sometimes if there is some reaction is happening which is either endothermic or exothermic, that can be also observed using DSC. So, DSC is mostly used to determine Tg, Tc and Tm, but if the polymer sample undergoes other thermal events like cross linking or vaporization or other reaction, that can be also monitored or probed by DSC, provided those events does not overlap with either Tg, Tm or Tc. Degree of crystallinity. Now, we will move to about degree of crystallinity. Degree of crystallinity is basically extent of crystallinity in a semi-crystalline sample, and it is of great technological and practical importance. Crystallization of a polymer from melt is accompanied by a reduction in specimen volume due to an increase in density, and this provides the basis of density measurements for determination of degree of crystallinity. So, if you know basically the density of a 100% crystalline polymer, then using that information and a 100% amorphous polymer, then using that information we can get the extent of crystallinity for a semi crystalline sample. Degree of crystallinity is generally either represented at volume fraction of crystals or a mass fraction of crystals, and they are expressed by these simple equations where this rho are corresponding densities. So, rho c is the density of a crystalline region 100% crystalline polymer, and rho is the density of amorphous region, so 100% amorphous polymer, and this rho is the crystallinity of the actual sample or the semi crystalline polymer whose degree of crystallinity we are going to determine. So, we can get this information, like we can get the degree of density of amorphous polymer easily if we cool the polymer sample from melt, then we can actually get a 100% amorphous polymer whose density we can measure, but 100% crystalline polymer is not possible. So, for that we can use some model or theoretical studies to find out from the crystal structure we can find out the density value or the value of rho c. So, rho c can be calculated and rho a can be obtained from experiment and rho can be also obtained from experiment. So, from that we can get this value of phi c and x c. The other methods to determine crystallinity is wide angle X-ray scattering, and this is generally for small molecule crystallite, small molecule crystals where we have a sharp crystalline peaks, and this is for small molecule perfect crystals, and in this case for perfect amorphous or 100% amorphous sample. For a semi crystalline polymer we can get a mixture of crystalline peaks and amorphous halo as shown here, and from the ratio of the area under these crystalline peaks and this halo amorphous region we can actually get the degree of crystallinity, which is given by the area under the crystalline peaks and divided by the area under the crystalline peaks plus the area under the amorphous halo, which will give the weight fraction of crystallinity or degree of crystallinity. We can also use DSC. From DSC we can, from the melting curve, from the area under the curve we can get the value of enthalpy of melting for that particular sample, and if we know or if we can calculate the enthalpy of melting for the pure 100% crystalline polymer from the knowledge of crystal structure, then from the ratio we can get the value of degree of crystallinity. This is very important because degree of crystallinity actually determine the measure by in a high extent the properties of semi crystalline polymers. There are other transition temperature which are more from a practical aspect, like heat deflection temperature. This is from a practical point of view that in application we do not measure Tg or Tm, is basically under some, if we use a polymer under some load, then at till what temperature it can sustain that load, that is more important than the Tg or Tm value for the inherent polymer. And of course, in that case the temperature till which it can sustain the load will depend on the load itself, and if the higher as the higher the load is higher, obviously the temperature will be lower in that case. So, heat deflection temperature or HDT is the temperature at which the material shows significant deformation of about 1/100 of an inch under constant load, and the load is usually 66 or 264 psi. As I described, HDT is dependent on the rate at and the rate at which this load is applied. So, this is more from a practical point of view. As you can see these pictures, as we increase this is the load, constant load, as we increase the temperature, at some temperature there is a bending happens. So, this is the temperature we call heat deflection temperature, and this will depend on the rate at which we are applying the stress and the amount of stress we are applying. Practical example, like if we talk about DVDs or CDs made up of polycarbonate and polymethyl methacrylate. In both these case the Tg is in this case is about 100 degree centigrade and in this case Tg is 145 degree centigrade. But look at the experiment done, this is 80 degree centigrade. So, in this case under the load of the CDs itself they actually becomes bent and non usable, whereas polycarbonate is unaffected at this temperature and this humidity. So, basically we should know the value of Tg and Tm for a semicrystalline polymer, but we should also keep in our mind what is the final application, and depending upon that we also need to generate or use some other thermal measurements like HDT and some other, there are some other Vicat Vicat temper, softening temperature. I am not discussing all those details. What I am just trying to mention that not only knowing the value of Tg and Tm will be sufficient from a practical point of view. From practical point of view, one should also do experiments which are close to the application where the polymers will meant for. Okay, now I will discuss about thermal degradation and which is given by or determined by thermogravimetric analysis. As the name suggests, it is a gravimetric analysis. Basically polymer samples are heated and the weight or mass of the polymer is followed using a balance. Now, it gives this thermogravimetric analysis or TGA gives information about thermal stability. Generally the temperature from which it start to lose its mass or weight we call decomposition temperature. Initial weight loss temperature, we can also use another term 50% weight loss temperature, where in the temperature at which 50% weight loss happen. We can actually keep the sample at a particular temperature, higher temperature, and follow the weight loss with time at a constant temperature, and we call that as isothermal thermogravimetric analysis. We can follow depolymerization process and loss of volatiles. We can follow fragmentation, thermal oxidation of additives, cross linking, or polymer reactions by thermogravimetric analysis. These are kind of indirect analysis, not direct analysis. It just basically weigh or find the mass of the sample with as a function of temperature. And in this case also generally inert atmosphere is used under nitrogen or argon, but if we want to find out oxidative stability of a polymer sample, then we need to do this thermogravimetric analysis in air or in presence of oxygen. This is a example of thermal stability of few polymers, PVC, polyvinyl chloride, PMMA, LDPE, PTFE, PI, and so this is the weight percentage. This is weight percentage and this is 100%. So, at some temperature it start losing weight and it almost becomes 0% or lose everything at extremely high temperature, and this temperature where the loss starts we call onset temperature, TD onset, and this temperature where 50% weight loss happen we call TD half or TD 50%, and this actually we can use this experiment to compare the thermal stability of different polymers. In this case PI is much higher stable than a PVC or PMMA. This stability also depend on the heating rate. If we heat the polymers faster, then as I described earlier that the polymer sample cannot follow the furnace temperature. So, effective temperature in the polymer actually phase is much lower compared to a actual temperature which is shown by the thermometer. So, if we heat faster, then the stability or the TD half or TD onset is actually we find little higher. So, generally we heat the samples around 10 degrees centigrade to have a balance. If we heat too slowly, then the experiment takes much longer time, which we cannot afford all the time. So, generally we heat about 10 degrees centigrade per minute standard heating rate to find out the thermal stability. So, this is a chart which basically gives the comparison of different thermal transitions like glass transition temperature, melting point, and we talk about heat distortion temperature HDT and decomposition temperature. For a semi-crystalline polymer, which at the beginning below at low temperature it is hard and glassy, stiff. First we get HDT, then we get TG, after that we get a range of temperature which is Tm, and then we finally get the degradation temperature. For a thermoset we get HDT and then TG, and we do not actually get Tm for this, and then we get degraded TD, degradation temperature. With this I will stop for this lecture, and in the next lecture I will talk about thermomechanical properties of polymer.